Okay, welcome to another video for TCX1004. This time around, we're going to talk about probability. So this is again going to be a two-part thing where first we talk about the basics of probability, and then next week we're going to sort of like carry off the concept and finish it up. So in this video, we'll talk about the basic stuff. So probability spaces, I'm going to introduce to you what they are, what's the notion of an event. We're going to talk about something called conditional probability, and we're going to talk about something called independence. Independence we won't talk about too much today. We'll sort of finish it up next week. Why? Because it's a lot easier to motivate examples via distributions rather than just by themselves. Okay, so sort of a small motivation to this part of the semester is to think about something called the Monty Hall problem. I'm not sure if you've heard of this problem before, but it goes something like the following. You're going to be at a game show where there's going to be a car and two goats. And the idea is that the car could be hidden either behind door number 1, door number 2, or door number 3. Okay, so the point is you don't know. They've randomly picked one of the 3 doors to put the car behind. Okay, and your job is to try to guess what the door is. But the game is a little more complicated than this. What's going to happen is that after you pick a door, let's say door number 1, the host of the TV show is going to pick one of the 2 remaining doors that you did not pick and reveal the one that has a goat behind it. So let's say this is the middle door. Okay, so based on this information, what's going to happen is that you have 2 doors remaining and the host is going to offer you an option. Do you choose to stay on your door or should you switch? Right, so some people think that there is a 50-50% chance that we win the car no matter what we do. Right, so in other words, it doesn't matter if we stay, it doesn't matter if we switch, it's a 50-50% chance either way. That's not quite true. Okay, so people do feel this way, and sometimes they think of this as a mind game between you and the game show host, and they think to themselves that it doesn't matter whether you switch or not. If the host tries to make you switch or whatever, maybe you should not switch and stuff like that. Well, it turns out that this is strictly losing, because the best strategy to do this is to actually always switch. Okay, and basically in the first part of this video, I'm going to show you why using probability theory. Okay, so we're going to make a few simplifying assumptions. We're going to assume that each door has a 1/3 chance of having that car. Right, so in other words, think of it this way, right? If the moment they start the show, they will sort of roll a dice or something, use a random number generator to pick one of the doors to have the car, so all of them are equally likely to have the car. Right, you can imagine how, if this is not the case, if some door has a slightly higher chance of having that car, you now have an advantage by picking that door. We're also going to assume that each door has a 1/3 chance of being guessed by the player. So in other words, when we're the player, we are also just going to roll a dice and randomly pick one of the 3 doors. Okay, and we're going to make this assumption that the door that's revealed is never the door of the car. Right, this is the rule of the game. Right, the game show host should never reveal the door that has the car behind it, because the whole point is to get you to guess it. Okay, so how we're going to model this for probability, let's try something simple. We're basically going to try to enumerate all possible sequence of outcomes. Right, so at the very beginning, the very first choice that is made is which door is the car behind. So let's say it could be behind either door A, B, or C. Now for each of these choices, right, we can also make a player choice, which is which door we choose initially, right? So it doesn't really matter what the car is, where the car is. We can make this choice sort of independently of where the car is. So, for example, we can make the choice A, B, or C in terms of which door we prefer. Similarly, if the car was behind door B, we could also choose doors A, B, or C. That's fine as well. Or even if it's the case that the car was behind door C, we could have chosen doors A, B, or C as our choice. Okay, so let me just shift this to the left a little bit so that I can make a bit more space. So far, what we've said is that there are 3 possible doors that the car can get behind, and there's 3 possible choices that we can make for the door that we prefer. Okay, so now things are going to get a little bit tricky. Imagine if the car was behind door A, and we also chose door A. In this case, the host can either reveal door B or door C to have a goat, right? Because the only door that the host can't reveal is door A, and by revealing either door B or C, this is completely fine. Okay, on the other hand, if the car was behind door A and we chose door B instead, right, then the host has to either pick door A or door C to reveal, but because door A has the car, the host is forced to reveal door C. Okay, so very similarly, if the car was behind door A and we chose door C, the only door that the host is allowed to reveal is door B. Okay, because the host cannot open our door and the host cannot open the car door, so the host must open the other door. Okay, so we can rinse and repeat this process if the car was behind door B, right? So if the car was behind door B, on the other hand, then and if we chose door A, the host has to reveal C. If we chose the same door as the car, so in other words, the car was behind door B and we chose door B, then it doesn't matter which door the host reveals, it'll be either A or C, and so on, right? And you can imagine how we can rinse and repeat this process again when the car is behind door C. Okay, so we can think of the sort of sequence of possible outcomes, right, as what we care about in terms of analyzing their probability. So what I mean by this is, for example, the car could be behind door A, we could have chosen door A, and the host could have revealed door B with some probability, okay? Or it could be the case that the car was behind door A, the player chose door B, okay, and the host revealed door C. It could also be the case that the car was behind door A, the player chose door A, and the host chose to reveal door C, right? So, and let's go through another example. The car could have been behind door A, the player could have chosen door C, and the host could have revealed door B, right? And you can imagine how we are going to basically just enumerate all the possible sequences of outcomes, right? So if I were to write this out in a sequence, we could have sequence AAB. In other words, the car was behind door A, we chose door A, the host chose to reveal door B. Or it could have been the case that the car was behind door A, we chose door A, and the host chose to reveal door C, so on and so forth, right? So if we list out all of the possible outcomes, you can think of this as our so-called quote-unquote sample space. Our sample space is a set of everything that might happen. Okay, so we have the set of possible outcomes, right? And again, think of this as the set of everything that might happen. And I argue that basically this is the very first step in analyzing, strategies or algorithms. Okay, so what we care about is, trying to figure out when the player might win. So this is what we want to do. This is our goal. Let's try a simple example first, right? So for example, if I want the set of outcomes that correspond to the car being behind door C, right? Then from this set of all possible outcomes, the subset that I care about are the last four, because those are the sequence of outcomes where the car is behind door C, right? So this is how you should look at the sample space. Okay, so we want to ask ourselves, if let's say the player decides to always switch, right? Which outcomes correspond to a win? Okay, so think of it this way. We're going to play the game, and after the host reveals which door has a goat, and he asks us, do we want to switch? We're always going to say yes, right? So think of it this way. The door with the car, okay, I claim that it's any outcome where the door with the car, the door that we chose, and the door reveal are all different. Why is this? Think of it this way. If the door with the car and the door that we chose are not the same are not the same door, okay, then after the third goat door is revealed, when we switch, we will definitely get the car. So for example, if you look at ABC, the car was behind door A, right? And then we chose to reveal door B. We chose door B, and then the host revealed door C to be the door of the goat. Now, if we chose to switch, we're going to switch from door B to door A, and we will win, right? This works the same even if we talk about if the car is behind door A, we chose door C, the host is forced to reveal door B, right? In which case, he's going to ask us again, do you wish to switch? And we will switch from door C to door A, and we will win, right? So in our sample space, these are the 6 outcomes that we care about. The ones where the any sequence of outcomes where the door with the car, the door chosen, and the door revealed are all different. Okay, so we're sort of making progress. We know which are the set of the sequence of outcomes or the set of outcomes that we care about are. Okay, we now need to ask what is the probability that it happens. Right, so first of all we've done is identify the events that we care about, but what about the probability that it occurs? Right, so let's go back to the tree. Okay, so again, I'm not going to be able to draw the full tree here, so you know, at least this way it's a bit more readable, right? But at the very beginning, again, the car could have been behind doors A, B, or C, right? This time around, I'm going to tag it with a probability, right? So there's a third probability that the car is behind any of the doors, right? Let's focus on the scenario where the car is behind door B. So if the car is behind door B, again, there was a third chance that we were behind any of the other doors, right? So A, B, or C. Okay, so again, remember that if the car was behind door B and we chose door A, then the host is forced to reveal door C, right? If the car was behind door B and we chose door B, the host is forced to reveal either A or C. And if the door that the car is behind door B and we chose door C as our choice, then the host is forced to reveal door A, right? So what is the probability that the host decides to reveal door C? Well, it's going to be 1. It's the only choice that he has, right? What about the probability that the host chose to reveal doors A or C after we chose door B? Well, let's just say half. Maybe he's indifferent to which door he reveals to you. Okay, and again, if the car is behind door B and we were behind door C, then the host is forced to reveal door A. That happens with probability 1. Okay, so which are the winning sequence of events we care about? Again, it's the ones where they are different. So for example, we care about the sequence of outcomes BAC. This happens with probability 1/3 times 1/3 times 1, which is 1/9. There's also the probability, the set of outcomes, the sequence of outcomes BCA. Now this happens with probability also 1/3 times 1, right? So based on this, let me simplify that for you. That's 1/9, okay? And the idea is that we've sort of computed the probability that if the car was behind door B, right, switching gives us a probability of like 1/9 of winning the game, right? So this is conditioned on the fact that the car was behind door B, but you can imagine how a similar computation works throughout the entire tree, right? Again, the ones that we care about are these events, the ones where it's either ABC, ACB, BAC, BCA, CAB, or CBC, right? And all of these you can check actually happen with probability 1/9. Okay, so if these are all of the outcomes we care about, right, it stands to reason that the total probability is just 6 times 1/9, which happens to be 2/3, which is the probability of winning if we switch. So it might be a bit counterintuitive, but you can actually mathematically prove that switching is actually the mathematically justifiable strategy. Okay, so that was an example of, let me mention what we just did, but that was an example of how to analyze problems from a probabilistic point of view. Okay, we listed out all the possible set of outcomes, we identified the subset of outcomes that we cared about, and then we figured out the probabilities for each outcome. Right, then the total probability, I reiterate, is just the sum of probabilities we cared about. Right, so again, our set of outcomes were these. We enumerated them, we listed them out, okay, and then from our set of outcomes, we identified the subset that we cared about. Right, we identified that it was going to be the ABC, ACB, BAC, BCA, CAB, CBA set of outcomes. Okay. And then what we did after that was that we went back and we analyzed the probability, and we argued that for each of these, the probability is 1/9, right? So if we summed up all of the probabilities, that's 6 times 1/9, which happens to be 6/9, which is 2/3. Okay, so formally, we're gonna say that so this is formal terminology, but a sample space S is the set of all possible outcomes. So in this Monty Hall example, right? We have all of these outcomes. There happen to be 12 of them, okay? An event is a subset of S. Okay, so an example of event would be, for example, the event that switching wins, okay, is given, again, because it's a subset, we are just identifying the 6 outcomes here out of the 12 that we care about. Okay, now again, it's not necessarily the case that any outcome happens with equal probability, right? In particular, in this case, I hope you notice that even though there are 12 possible outcomes here, right, some of them happen with probability 1 over 9, some of them happen with probability 1 over 8, right? So again, each outcome is associated or related to, if you want to use a relation, is related to a unique probability value between 0 and 1. Okay, and the idea is that the probability of an event is simply just the sum of probabilities of each outcome in the event. So again, the probability of the event of winning, okay, would just be, since all of these have probability 1 over 9 each, then this is just 1 over 9 times the number of outcomes that we have. You might imagine how this might be different, but in this case, all of them have probability 1 over 9. So really, it's just 1 over 9 plus itself 6 times, which is 2 out of 3. Okay, so now that we've mentioned a bit about the terminology, let me talk a little bit about some of the other rules that we have. Okay, so the probability of any outcome is going to be greater than or equals to 0. In other words, we are only going to list an outcome if it has a non-zero probability of happening. So no such thing as a negative probability here. Okay, the sum of all possible probabilities is exactly 1. So in other words, if we went through the entire sample space, okay, and we took every outcome and we added up their probabilities, okay, then the sum has to be equals to 1. Think of it this way, we are basically saying that some outcome is guaranteed to happen, we just don't know which. Okay, so a few more sort of like rules about probability. Since we talked about A and B as events, and we mentioned that events are basically just sets of outcomes, if you remember from last week, we talked about counting and we said that if A and B are disjoint sets, then the size of A plus B is basically just A union B. Okay, well, it turns out in probability, we can say something very similar, where we say that if A and B are disjoint events, so again, think of events as sets of outcomes, then the probability that either A happens or that B happens is given by the probability of A plus the probability of B. Okay, if you also recall from last week, when we talked about subsets, we said that if A is a subset of B, then the B set minus A, the size of this is basically size of B minus size of A. Okay, so again, if S is our event space, think of this as the set of all possible outcomes, and A is some event, which is some set of outcomes, okay, then, oh, that's a typo. That should be, since A is a subset of S. That's typo right here. Let me see if I can fix that. So there should be A subset S. Sorry about that. Okay, but since this is true, since A is a subset of S, that's what it means to be an event. Okay, then it has to be the case that the probability that S set minus A, think of this as basically saying the probability that an outcome that is not in A occurs. Okay, by definition happens to be the probability of S minus the probability of A. Okay, and from the previous slide, we would have talked about how this basically means 1 minus the probability of A This basically means 1 minus the probability of A, which we're going to write in this way. So there's going to be a bar above A. Okay, so what is the intuition behind this? The intuition behind this is that A is the complement event, right? Think of this as saying the probability that A does not happen. So for example, maybe we wanted to say, what's the probability we didn't win? In other words, the probability that we switched and we got a gold. That's an example of a complement event, right? Okay, so let's say that we had let me sort of like work these through with a few examples. Let's move away from Monty Hall. Let's try something a bit simpler, right? Let's say we had three numbers, 1, 2, and 3, and let's say that we're going to sample a permutation uniformly at random. I stress on uniformly at random to permute the numbers. Okay, so what is the probability that after permuting, number 1 stays at position 1? Okay, so this sounds kind of complicated, but let's break it down. Again, we need our set of outcomes or our event space, right? Since we are sort of sampling a permutation uniformly at random, okay, then what we're doing is that basically we're saying that there are actually 3 factorial possible outcomes, right? Either we get the first permutation, or we get the second permutation, or the third, the fourth, all the way into the sixth. There's 6 of them, right? Because 3 factorial is 6. Okay, so again, I emphasize on the fact that this is done uniformly at random because we are sampling a permutation uniformly at random, right? If we had a set of outcomes S, on the screen here we have 6 of them, then the probability of any outcome is 1 over S, right? So in other words, with 6 outcomes, the probability of any outcome happening is 1 over 6. Okay, so the probability that after permuting, number 1 stays in position 1 happens to be if we obtained either of these 2 outcomes all the way on the left of the screen. Either we got permutation 1, 2, 3, or we got permutation 1, 3, 2. Right? So we have 2 possible outcomes here. This forms our event. Right? The event, the number 1 stays in position 1. Okay, so there's 2 possible outcomes in our event, and the probability of this event happening is the sum of the probabilities of the individual outcomes, which is 1 over 6 plus 1 over 6, which is 1 over 3. Okay, what about the probability that after permuting, the first item is not at position 1? So think of this as the complement event. Well, there are a few ways to do this. One way is that we already know the probability of the first item being in position 1, which happened to be 1 over 3. So we could just say 1 minus 1 over 3. Okay, so the other way of doing it is to manually count it. In other words, you can manually count the outcomes where the first item is not in position 1, and if you did, you would also realize that this is just 2 over 3, so it actually works out to be the same thing. Okay, the last one. What about the probability that after permuting, the first item is in position 1 or in position 2? Right? So there are 2 ways to do this. One way is you could just manually count it. You could just say that there are these events that my event consists of 4 outcomes that we care about, right? The ones that I've sort of drawn out in the green box here. There are 4 of them. There are 6 total outcomes. So 4 over 6 is 2 over 3. The other way of doing it is that you might notice that these events are actually disjoint. I can think of this as 2 events. The first event is first item is in position 1, and the second event is first item is in position 2. Right? Because these two sets of outcomes are disjoint, we can actually just add them up. In which case it would have been 2 over 6 plus 2 over 6, which actually also still gives us 4 over 6 or 2 over 3. Okay. Okay, so let me elaborate a little bit on this whole uniform distribution thing, even though we will talk about it in detail next week. Right? This is the simplest kind of distribution. In general, if we are uniform over some event space S, okay, then the probability of a specific event E happens to very simply just be the size of the event set divided by S, right? So you might have remembered this from the previous one with the permutations, but let me just show you an example just so that we're clear. Let's say that we're given a dice that gives either 1, 2, 3, 4, 5, or 6 uniformly at random. So again, I emphasize on the fact that we are assuming that the dice is fair and is uniform. Okay, so what is the probability that a dice gives us an even number? Okay, so for example, let's just say, so right now my outcome space is 1, 2, 3, 4, 5, 6. Okay, and the event that a dice gives us an even number would just be the set of outcomes 2, 4, and 6, because those are the even outcomes. Okay, now because the dice is uniform, right, like we said before, this is just the size of E divided by the size of S, which actually happens to be 3 over 6 divided by 3 over 6. Okay, so that was a uniform distribution. So again, we'll elaborate more on that next week. But now that we've talked about probability, the more important thing to talk about is conditional probability. Right, so probability by itself really is at this level just counting the number of outcomes and doing something with it. The more interesting thing to talk about is questions like the following. Given that the event that a dice rolled an even number, what is the probability that the dice rolled a 4? Or something along the lines of, given the event that after flipping 3 coins we saw 2 heads, what is the probability that the first coin flipped turned up heads? Right? You can imagine how that there is this sort of like added condition that we have on our probability, right? So this is actually super useful. But before I even show you how to compute those things, let me talk about a more motivating example for like testing, right? So let's say that this is the classic example for conditional probability. Let's say that we had a medical test for a condition, right? So in other words, like some sort of ailment, some sort of illness, maybe COVID, okay? So tests in real life are not perfect and they can make errors, even though it's very, very unlikely, right? But this is something that scientists need to account for. Okay, so what kind of errors can you make? Well, for one, the test could report positively that you have a condition. So bear in mind, when we say positive, we don't mean it's good news. We mean affirmative, right? That the test wants to confirm, so it's positive that there is a condition, even if you don't. Okay, so when the test says yes, even though you don't have a condition, we call it a false positive because it's not a real positive. Or the other way around, a test could report a negative when you have a condition, right? So when you have a condition and it reports that, when you have a condition and it reports yes, then this is what we call a false negative. Okay, so this actually extends beyond medical tests, right? So imagine, for example, you had to write an image classifier that tells you whether or not the picture contains an apple. So there's a chance that the classifier reports a false positive. In other words, the image has no apple, but the classifier is going to say yes. Or there is a chance that the classifier reports a false negative, right? In other words, the image does have an apple, but the classifier doesn't say so, right? And this is something that we need to deal with in AI and machine learning, right? The idea of not being correct 100% of the time. There is a chance that we will say yes when we're supposed to say no, or the other way around, right? So yeah, beyond medical tests, this is something we deal with in computer science as well, right? So for example, we might want to know something like the following. Given that a test reports positive, what is the probability that it actually is a true positive? Or given that a test reports negative, what is the probability that it is a true negative? In either case, right, you can imagine how there is still this whole conditioning thing going on in our probability. What is it? How should we compute the values? Or how should we understand this, right? Okay, so let's go into conditional probability. Conditional probability in general is written in this way. We have a probability of some A given some B, okay? And think of this as the probability of the probability that event A happens given that event B, we are promised that event B happens. Okay, so there is no notion of before or after here. There is no notion of time. It's just that I promise you that B happens. Okay, what is the probability that event A happens as well? Okay, so the way that we would write it is like this. This is the formula for conditional probability. Okay, so what is at the top here? Think of this as the probability that event A and event B happens. Okay, and think of the one at the bottom. Think of the one at the bottom as the probability that event B happens. Okay, so it might be a bit counterintuitive right now. So let me show you an example, right? So let's go through the previous one. Given the event that a dice rolled an even number, what is the probability that a dice rolled a 4? Okay, so in other words, I promise you that the dice rolled an even number, and this dice could have produced 1, 2, 3, 4, 5, 6, but it produced an even number. What is the probability that the dice rolled a 4? Okay, so we're gonna let A be the event that the dice rolled a 4. We're gonna let B be the event that the dice rolled an even number. Okay, so again, recall that events are really just sets of outcomes, right? So in other words, A here is going to be the set containing outcome 4, and B here is going to be the event, the set that contains outcomes 2, 4, and 6. Okay, so we want the probability of A given B, right? Given the event that we rolled an even number, so the probability of A given B, okay? And like I told you, this is basically just the probability of A intersect B divided by the probability of B. Okay, so let's work this out manually. So A intersect B is 4 because, well, A set only contains 4 and B set contains 2, 4, 6. So it stands to reason that the intersection is the outcome 4. Okay. So the probability that of A intersect B happening is 1 over 6 because we're going to assume that the dice is fully uniform. Okay. So we only have one outcome out of the 6 possible outcomes. It stands to reason that this is 1 over 6. Okay. What about the probability of B? Well, that's just the size of B divided by the number of possible outcomes, which is 6. So this is just 3 over 6. So if we work this out as a fraction, this becomes 1 over 6 divided by 3 over 6, which is actually just 1 over 3. Okay, so that's kind of how this formula works. And if you want some visual intuition, let me draw two sets for you. So here's the idea. The probability of A intersect B is really the probability of the events in the A intersect B region. Okay, and the probability of B is basically the probability of the events that happen in the B region. Okay, so to reiterate my point, A intersect B is this side and B is this side. So probability of A given B is really the ratio of the pink side divided by the green side. Okay, so more importantly, note that we basically aren't counting events of A that are outside of B. Okay, so let me show you an example with testing. So let's say that I want to make a classifier to take an image and report true if the image has an apple. Okay, so given that the classifier actually does say yes, there is an apple, what is the probability that it is a true positive, right? In other words, the classifier was correct when it said so. So again, we want to use this notion, right? Or more importantly, this fraction. Okay, and you can think of A here as the probability was actually positive, and think of B here as the event that the test reports positive. Okay, so there are a few things you might want to think about. Okay, so probability B by itself is the probability that it's actually positive. Okay, so what is this? This is just the number of images that have apples. Okay, and probability of A intersect B is the probability that a picture has an apple and the classifier says so. Alright, so how do we get this kind of information? Right, let's try doing it this way. Let's say that we prepared a data set of 10 pictures, 6 of them have apples and 4 of them do not have apples. Okay, so of the 10 pictures, right, how often the classifier said yes and there was an apple in the picture, right, is basically the probability of A intersect B. Right, so let me show you what I mean. Let's say that I have 10 pictures here, okay, and 6 of them are apples. Okay, and of the what our classifier said was no, yes, no, yes, no, right? So in other words, it basically said yes or no to some apples, it said yes or no to some pictures of non-apples, right? And we want to find out what is the probability that when our classifier says yes, it actually is a yes, right? So we want to find out what is the probability that it's positive, right, when we're promised that the classifier says it is. Okay, so one way to do this is to basically go out and count the number of outcomes where the classifier says positive and at the same time it is positive, right? So in other words, we want it to be the outcomes where there are apples and the classifier said yes to them, right? So of our example here, there are going to be 4 of these. Okay, we also need the probability that the classifier says positive. So of the 10 pictures, it said positive 6 times. Okay, so 4 divided by 6 happens to be 2 over 3. Okay, so there's an alternative way to do this, and it basically uses something called Bayes' rule. So this rule is actually super useful. Okay, so let me explain what this does. It's basically saying that the probability of A given B can actually be rewritten as the probability of B given A times the probability of A divided by the probability of B. Okay, so again, what we care about is the fact that when the classifier says that we have an apple, we indeed do have an apple. Okay, so in terms of this fraction, what we care about again is the probability that a classifier has an apple. Okay, and given that a classifier has an apple, given the image where a classifier has an apple, the classifier says so. So in other words, we flipped it. Okay, so in other words, now we're saying that, okay, the opposite side would be to say that we know that there's an apple. What is the probability the classifier says we have an apple? Okay, and we multiply this by the probability that, you know, we have an apple. Okay, that's a lot of apples. But basically, again, according to this example, here's how it works. If we wanted to use this fraction instead, okay, then what's the probability of A? Well, this happens to be 6 out of 10 because we had 6 apples. Okay, what's the probability of B? It's also 6 out of 10, a bit of a coincidence, but it's 6 out of 10 because the classifier says, you know, it says has apple 6 times, right? So if you actually check the example, you would see that there's 6 green ticks, right? So that's why 6 out of 10 times it has actually said so. Okay, now this quantity is a bit more interesting. So the probability that that the classifier says that there is an apple, given that there is actually an apple, right? So we have 6 apples here, and of those 6 apples, right, out of those 6 apples, 4 times did the classifier say, yes, there is an apple. So that's 4 out of 6. Okay, so if we were to substitute these quantities in, that's 4 divided by 6 times 6 over 10 divided by 6 over 10, which actually still gets us 4 over 6. Okay, so we arrived at the same number through 2 different methods. Maybe that's a bit unsurprising, but it's an alternative way to do it. And at this point, you might be asking, why do it this way? Why do we have 2 formulas for the same thing, right? So let me give you an example. Okay, so for example, let's say that we know, here's a different example. So let's say we know, for example, 5% of the population have some condition. Let's call that condition C. So it's some kind of illness, some kind of sickness. Okay, we know for a fact that if we administer the test on a positive patient, they have a 90% chance, the test has a 90% chance of reporting it as positive, right? So again, given that there is a positive patient, the probability that the test says yes is 90%. Okay, let's say that if we were to just administer the test on anyone, regardless of whether they're sick or not, right? We tried a bunch of people, and it turns out that it reports them with probability 23.5%. Okay, so let's just say that now we took the test and it was positive. Okay, so what is the probability that we have condition C? Okay, so in other words, again, what we really care about is letting A be the event that we have condition C, letting B be the event that the test said positive, and we care about finding the probability of A given B, right? In other words, given that the test said yes, what is the probability that we really do have the condition? Okay, and based on the information that we have so far, right, we can't really figure it out based on the probability of A intersect B divided by B, right? On the other hand, we can actually use this fraction and it'll be very helpful. So let me show you what I mean, right? So because 5% of the population has condition C, right, we can basically say that the probability of A is 0.05. Similarly, because the test administered on a positive patient has a 90% chance of reporting as positive, in other words, given A, the probability of B is 90, we can replace the probability of B given A with 0.9. And lastly, we know that if we administer the test on anyone, the test reports positive with 0.235, chance, right? So we can replace probability of B with 0.235. And if you try this out and you work this out, it should be roughly 0.19. In other words, this is basically saying that, given that the test said positive, we might not be 100% sure that we actually do have a condition. Now, if you still have your COVID test kits from, a few years back, you might actually want to look at the box, because I think the box actually does tell you what the false positive and the false negative rates are. So now you know. Now you know that if you had to take this test, what is the probability that you have it, right? So Fun fact, when I got COVID many years ago, when I took the test and the test hit positive, I actually did whip out a calculator to try to figure out, given that the test hit positive, how confident am I that I do indeed have COVID? In fact, I think I worked out from the test, the probability was something like 87% or something like that, based on the test kit that I used. Yeah. Okay, so let me just try to elaborate on the example a little bit more. Okay, so let's say that I had a table, and the table here basically rounds up a bunch of results that we did, right? So we have in total 1,000 participants. Let's say we know for a fact that some of them were actually positive, some of them were actually negative, and we want to test the performance of our new testing kit, right? So let's do a few basic values, right? So let's say that A is the event of actually being positive. In other words, nothing about testing going on here. Okay, let's say that 50 out of 1,000 people that we had, we know for a fact are positive. Okay, then the probability of A, again, is just the number of people who are actually positive. Here, that's the total value, divided by the total number of people that we have, which is 1,000. So that's 50 over 1,000. Okay, again, as a reminder, A complement is the event of being actually negative, right? So if you want to work out what the probability of A complement is, that's just 1 minus the probability of A itself, which happens to be, if you work it out, you realize this is the same thing. It's 950 divided by 1,000. Okay. Now the probability, the probability of B, again, is the event. B is the event of the test being positive, right? So in other words, all we care about is the number of positive tests divided by the number of total participants, which happens to be 235 divided by 1,000. And again, B complement is the event that the test is negative. So you can think of this as just 1 minus the probability that the test is positive. You could also just manually count 765 divided by 1,000. They both line up to be the same thing. Okay, but perhaps the more interesting quantity again is this one, right? So for example, if A is the event of actually being positive and B is the event of the test being positive, right? Think of this as basically us asking, if we know someone's positive, what's the likelihood that the test is actually going to tell us that, right? So based on this table here, okay, to calculate the probability of the test saying positive, given that we know for a fact that the person being tested, the patient, is actually positive, then instead of dividing by 1,000, we should be dividing by 50, because that's the number of positive people, right? And of the 50 positive people, the test said yes to 45 of them, so this is just 45 divided by 50, right? Very similarly, we could have asked something like, let's say for example that we know for a fact that the test said positive, right? If we know for a fact that the test said positive and we want to ask ourselves, what is the probability that the person is actually positive? Okay, then we now have to instead divide by 235 people who we know are the ones that the test said positive to. Okay, and the number of people who are actually positive happens to be 45. So that's 45 divided by 235. Right? So again, very similarly, if I wanted to say that we know for a fact, I promise you that the test said negative, what is the probability that we are actually positive, right? Then this would just be finding the number of actually positive people, that happens to be 5, and dividing by 765, which is the total number of people that the test said negative to. Okay, so now that I've mentioned some of these quantities out as examples, okay, think of the probability that the test said yes when we know for a fact that the person is yes as the true positive rate, when the test said no when the person actually has the condition, we're going to call it the false negative rate. On the other hand, if the test said yes even though we don't have the condition, that's called the false positive rate. And the probability when the test said no when we are actually no is the true negative rate, right? So in other words, the first and the false case is good, the second and the third case is bad. Those are the false cases. Okay, so now that we've talked about that, let me just expand a little bit more and finish up something called independence. Okay, so we've talked about events being dependent, right? In other words, we've talked about conditioning on events, their probabilities might change, okay? But we need to think about when two events are unrelated in some sense. And again, this will be very introductory right now. We will talk more about this in the next week. But how do we say that two events are unrelated, right? So for example, let's say that I flipped two different coins, and let's say that we make this assumption. So this has to be an explicit assumption on our end, right? We actually have to assume this. We're going to assume that the outcomes should not affect each other, right? So we're going to say that events A and B are independent if either the probability of B is 0 or the probability of A given B is just the same as the probability of A itself. Okay, so what is going on here? Think of this as the intuition. It's basically saying that given that event B has happened, the probability for event A remains unchanged. There's an alternative way to write this, and you can actually prove that they're the same formulation. We can also say that events A and B are independent if the probability of A intersects B. In other words, the probability that both things occur is the same as if is the probability of A multiplied by the probability of B. Okay, so for example, let's just say that I had two different coins. Let's say that they are independent. I'm going to assume that they're independent. Let's say that coin 1 produces hits with probability half and otherwise produces tails. Let's say that coin 2 produces hits with probability half and otherwise produces tails. Now we're going to assume that coin 1 and coin 2 are independent. What is the probability that both coins produce tails? Well, the probability, we're going to write it in this way. We're going to say that the event that coin 1 returns tails and the event that coin 2 returns tails. Okay, so what is this? Well, because they're independent, we can just work this out to be the probability that coin 1 returns tails times the probability that coin 2 returns tails. And by what we said about the coins, this just so happens to be half times half, which is 1/4. Okay, so just to show you that things aren't always that simple, I'm going to show you a set of three coins where they are seemingly independent, but not. It's independent in some way, but not in others. Okay, so again, we're going to have coin 1 and coin 2 be the same as before. They produce hits with probability half. But coin 3 is a bit special. It's going to look at coin 1 and coin 2, and it's going to say the following. Okay, in other words, we're not flipping coin 3, but it's going to say that if there are exactly 1 hits, coin 3 will also return hits. Otherwise, it will return tails. Okay, so to map this out a little bit, right, coin 1 with probability half produces hits or tails. And for each of those, coin 2 with probability half produces either heads or tails. Okay, now coin 3 again, right, has to look and see what the previous two outcomes were before deciding what it wants to be. Right, so if it sees 2 hits, it will produce tails. If it sees a hits and a tails, it will produce hits. If it sees a tails and a hits, it will produce hits. And if it sees 2 tails, it will produce tails. Okay, so we might want to ask something again, like what is the probability that coin 1 produces hits and coin 2 produces tails? Right, you can try this for yourself. You can walk through the tree. That happens to be half times half, which is 1/4. Okay. You could also ask something like, what is the probability that coin 1 produces hits and coin 3 produces tails? Well, that happens to be these two things, and if you walk the tree, this happens with probability half times 1, which is 1/4. Okay, or you could ask something like, what is the probability that coin 3 produces hits? Right? Now there's two ways to walk the tree here. Right? Either you can go up and then down and up again, so in other words, hits, tails, hits, or you can go tails, hits, hits, right? So each time you do the walk, it's half times half, and there are 2 possible leaves in this tree for you to reach coin 3 with hits, right? So that happens to be half times 2, which is half. Okay, now the probability that coin 3 produces tails instead is a very similar argument, but you walk a different part of the tree. It's still half times half, and you can do this for 2 possible ways. Either you go up and up the tree, or you can go down and down the tree, right? In which case you still produce the same tails. So that's half times 2, which is also half, right? So coin 3, the probability that coin 3 produces heads or tails is half, right? And we can even ask something like this. We can ask, can we see that the events coin 1 produces heads and coin 3 produces tails are independent, right? So in other words, what I'm asking is, what is the probability that coin 1 produces heads and coin 3 produces tails, right? And if you check the tree, it's basically, it has to be from up and up, right? In other words, coin 1 produces heads, you go up the tree. Okay, now from here, notice that if coin 2 produces tails, coin 3 will produce a heads, which is not what we want, so it must go up. So it has to be half times 1, right? Which gives us 1/4. Okay, so this is the probability coin 1 gives us heads and coin 3 gives us tails. Okay, now let's work out the other two probabilities manually. So if you remember from the previous parts, we can say that coin 1 produces heads with probability half and coin 3 produces heads with probability half. And if you multiply the two of them, that also gets you 1/4. Okay, so they are independent events. It doesn't matter if coin 3 decides its behavior based on coin 1. Okay, the fact of the matter is that the probabilities, these two probabilities, are the same. Okay, so they are independent. Okay, so why did I say seemingly independent? Because this is the interesting case. Instead of asking for 1 and 3 or 2 and 3, let's say we ask for 1, 2, and 3 at the same time. Okay, so in other words, let's say that I have the events coin 1 produces heads, coin 2 produces tails, and coin 3 produces tails. Are they independent? Okay, so first of all, note that coin 1 producing heads, coin 2 producing tails, and coin 3 producing tails, the probability has to be 0. Remember, this is because coin 3 only outputs tails when both coin 1 and coin 2 are either both heads or tails. Because now we are in a case where coin 1 has heads and coin 2 has tails, coin 3 must produce heads. So in other words, the probability of these three events happening together is 0, right? So heads, tails is impossible. Okay, but if we looked at the probabilities individually, they actually work out to be half, half, and a half. So if we multiply the probabilities individually, okay, this would be half times half times half, which happens to be 1/8. Okay, so these two probabilities are now not the same. Okay, so are these three events independent? Can we say that they are independent? Well, no, we can't. Okay, so hopefully this was a motivating example to show you, the difference between independent versus non-independent events. I will also mention that, I've mentioned this just now, but independence is really an assumption that people make. It's a bit of a philosophical choice, if you will, to some degree, whether we decide to think two events should be considered independent or not. Because in real life, there is no telling whether flipping a coin, let's say, 50 kilometers away should affect the outcome of a different coin being flipped, in a different country, let's say, right? We would like to philosophically argue that it is true that they should be independent coins, independent flips and independent outcomes and independent events. But this is a philosophical choice you have to make, right? You have to say that it's a philosophical choice to say that we think it's reasonable to assume that these events are independent, right? So in other words, independence is typically an assumption that we make before we start analyzing our distributions, okay, rather than looking at like a thing and then saying that we can prove that they're independent. Okay, so this basically rounds up what I have for you this week. It's a lot of probability basics, it's a lot of just counting, right? And hopefully in the tutorial, things will make a little bit more sense. We will get you guys to compute a few probabilities. But if not, the plan for next week would be to cover probability distributions. So there will be 3 there. There will be the geometric, there will be the Bernoulli, there will be the binomial. These are the most common distributions I think you will see. And we'll talk about a few bounds. So we'll talk about the Markov bound, the Chebyshev bound. We'll talk about something called Jensen's inequality. These are like the most useful bounds that I know that we use in computer science. And that will basically round off all the topics that we should be covering. Okay, so that's all I have for you today. See you next week.